I respectfully challenge Terrence Howard and his claim that 1 times 1 equals 2. And I propose that 1 squared can actually be proven to equal 4, and that 1 cubed is 6. Terrence Howard has been showing up all over the place with his personal discoveries around how the universe is woven together. I love that he references the work and writings of 2 men and even spoke their names in the same sentence, as I often do. Both Walter Russell and Victor Schauberger are household names for my family due to the ease in which each one of them contributed to my growth as a thinking human. They allowed for the comprehension of energy and matter to find equilibrium in my thoughts, which had been previously distorted by Newtonian physics and Euclidean space. Up until I opened the book The Secret of Light by Walter Russell and the book Living Waters by Olaf Alexanderson, I experienced a certain degree of cognitive agitation and atrophy due to the incomplete analysis of things delivered as fundamental truth in public school curriculum. I applaud the work Terrence Howard has done and his passion for presenting the work of Russell and Schauberger, as well as his own revelations. When listening to his presentations on YouTube, I could not resist the urge nor wait to join the conversation, especially because I must challenge several points that Terrence makes on which I sense a divergent outcome and reality. So here we go. The central issue or incongruency from my humble perspective has 3 parts, and the first part is dimensional. As an ignored habit, whenever we move from one-dimensional calculations, as in a number line or ray, and move into 2-dimensional shapes, we do so without the courtesy of changing our grammar or making a point to otherwise signify that we have done this. Let me demonstrate. Here is a basic number line, beginning with 0 at the left and extending to the right. The first marking from 0 is an arbitrary distance from 0, and each marking after that is theoretically equidistant apart, creating a specific, consistent rhythm. Across the modern world, in all so-called developed societies, we group these markings in packs of 10, and we group the 10s in packs of 10, and we group those packs of 10 into packs of 10, and so on. We call this invented representation of quantitative value a number line. As we move from the single point, which has no value, no mass, no volume, nor weight, temperature, frequency, etc., and move in the opposite direction towards the right, we say that we have a positive gradient, and any value extrapolated from this line increases as you move to the right. I just made something very basic sound quite complicated because it is actually a little more than just basic. So now let's do a calculation using this line. 1 plus 1 equals 2. 2 plus 2 equals 4. Oh, but wait, what are we actually seeing and speaking here? Before I can go on about the issue with dimensions, we must address the second issue of association, or in our predicament, disassociation, and our prime unit. So, what is 1? 1 must be associated with something in order for it to be meaningful. Even in the wide world of mathematics, something is always being calculated, even if it is only thought of as an increment or an integer. 1 chair, for example. 1 person, 1 potato, 1 gallon, 1 mile, 1 degree, 1 increment. The 1 on this number line is placed here arbitrarily, as it sits somewhere between 2 infinite poles of expansion and division. You see, 1 is a noun and also a transition. The placeholder for 1 on this number line is an infinitely small point, which actually has no size at all, and it would be very easy to miss with a dart because the place where it sits on this line is infinitely specific and can only be found conceptually. 1 is both a telescope and a microscope. It is the lens that we have created to detect quantitative value in our universal experience. When you increase the basic units, you can increase them forever. And when you subdivide this basic unit that we call 1, you can also do this forever. There is no absolute greatness or absolute smallness because we can only define what is relative to a previously defined point in space or in material or the object itself. There is also directional infinity. If we draw the mirror image of this number line, which has thus far been a ray moving in one direction from stillness, we will now have what is called a line, which is infinite in both directions, unless you define 2 points along this line and consequently create a line segment. We can now see the negative sequence of the infinite strand of equivalent basic units counting in the opposite direction of our original line that began at the centering point of zero stillness. On this landscape, we are able to move a sliding ruler along to detect positive and negative gradients, spans of value, or the amount of potential between, say, 2 points of electrically charged particles. Recognize, too, that we can extend a ray outward in any direction from any point in space. But it's important to intuit what 1 is. Like, what is 1 right now? Nothing. 1 is nothing to us when we are not speaking of it or cognizant of it. So what makes 1 relevant? To what are we applying it? In this calculation, we can say that 1 is 1 increment on this number line. The check mark on this line is an object. It is objective. It is also subjective in that it will be subject to our calculations, which are actions made upon it. It is the object of all calculations, and it is the subject of the number sentences we think and speak. This calls out our grammar issue, which I will tie in a little later. The 1 on this line has been defined as the distance between the 0 cross point symbol and the mark I placed on the line. This becomes the basic unit because I have defined it. It is now defined. We could rename our base unit. We could name it chair instead. And now on this number line, we have chair. And we can multiply chair by 2 and verify that we now have 2 chairs as the result. Note that our English grammar provides for a change in syntax to keep congruent with the plural form of chair, which is chairs. This works, yes? When we multiply, I observe the following things to be true. The number that we speak, or the calculation we apply to the subject or object, is an action. The subject/object is being acted upon. So 3 times chair equals 3 chairs. Right. Great. Good. Let's multiply now, which is really just a condensed form of adding value, whether that value is moving toward the right or the left. Either way, on this number line, increase and decrease happens at the same time as we move in either direction. This highlights one contradiction I have in my understanding of the Terrence Howard mathematical conceptual presentations. To be concise, to multiply means a simultaneous increase and decrease, not simply an increase in quantitative value. And this works in conceptual numbers, as well as the universe per Walter Russell's understanding. We can multiply or apply a factor of 2 to chair, and the result or product of this factory is 2 chairs. If we apply a factor of -2 to our object, the result is -2 chairs. This is relevant in both the human world and in conceptual number space. This is useful and relevant, as with every credit, there is an equal and opposite debit. Now let's try applying a factor of 1 to chair. Now wait, we're not using 1. We replaced 1 with chair, remember? Okay, so let us apply a factor of chair to chair. Well, chair is already chair. It won't be affected by what it already is. To affirm this, let us speak and think of applying the factor of 5 to chair. Can we multiply 5 chair to chair? No, the syntax is wrong. 5 chair is not an action. 5 is an action, and chair is the subject, and thus we don't multiply chair to chair along this one-dimensional number line. In keeping with proper grammar and syntax, one of the 2 chairs in our number sentence has to be the action, and the other has to be the subject or object. But this cannot be the case in one-dimensional number lines. Let's look at addition, where it appears that we are not acting upon a number, rather we are finding points on the number line given the proper directions to get there. The number sentence must still have proper grammar and syntax, and so if we look at chair added to chair, or say that chair is with chair, rather than an action affecting an object or unit, we are describing how many units are of importance. When there is a sequence of additions and subtractions, we are moving the needle up and down the number line in respect to the positive or negative value gradient. Let's try this again. Chair plus chair equals 2 chairs. Chair times chair equals what? Like, what's tree times tree? I appreciate that Terrence Howard is pointing out something that is potentially nefarious when multiplying a nickel times a nickel and getting 0.05 times 0.05 with 0.025 as a result. Whilst a nickel represented by 5 cents, when you multiply 5 times 5, this gives you 25. And comparing 0.025 to 0.25, the 0.25 is the larger number and better deal maybe, or greater value with a positive gradient. But in general, we do not multiply an object by an object. The grammar and syntax in this nickel example is all over the place. We have to clear this up so we can know and hear the difference when we are either talking about subunits of the basic prime unit or if we're talking about whole units. We will get into subunits of the basic prime unit here shortly. And I'm basically done with this bit about multiplying a nickel by a nickel, which gave me the fits as soon as I heard it. I gave it quite a bit of consideration to become aware of all the ways this radical maneuver might be applied to my finances or anyone else's, and I did not discover where it would occur. And that doesn't mean it doesn't. I just haven't discovered it on my own. If someone is calculating your share of the pie by multiplying a certain sum by a value of less than 1 or a subunit of $1, that would be shady. Moving on. Let's look at 2 twos. This segment represents 2 ones or 2 chairs or 2 increments and so on. We can now count segments. Segment becomes a prime unit. This is one segment of 2 increments. Every other segment maintains the same increments. The segment equaling 2 base prime units is now the subject or object. We are going to act upon this segment or value and decide that we want to see a visual representation of 2 of them. Here we go. We now have 2 segments, which gives us 2 by its virtue. But if the answer that is meaningful resides within the basic units, then we would give the answer in basic units, which is 4. I can now give an example where it seems like we multiply objects by objects. Here is the example. We have baskets of strawberries. Each basket is full, and a full basket holds 100 strawberries. There are 10 baskets that we're counting the strawberries they're in. First question, what answer are we looking for? We're looking for the number of strawberries. Our answer will be given as a number of strawberries. Strawberry will be the base unit. We cannot multiply strawberry by strawberry, but in a sense, we will be multiplying strawberry by basket, but not really. We're multiplying strawberries by a value, not by an object. We multiply strawberries by the number of baskets, not by basket. If we were determining how many baskets there were by dividing the number of strawberries by 10, we would have our answer in units of baskets. Back to the line. We can multiply or act upon our object, a group of ones equaling 2 ones, or let's just call it a segment. And we can write it this way. 2 times 3 equals 6, where 2 is the action, 3 is the object, and 6 is the answer given in base prime units. Or we can say that 3 is the action, and 2 is the object, and 6 is still the answer in base prime units. On to the controversial topic of square root. I would like to prove that the square root of 1 is completely rational, but the way that we present it is not. Here we go. On our one-dimensional number line, let's see, 1 times 1 equals 1, but why? Because the action of 1 upon a single object or unit gives us 1 object or unit. And now let's try 1 squared. 1 squared equals 1 square, a new prime unit arising in two-dimensional space based on its one-dimensional roots. Squaring is an action that occurs along two perpendicular axes. You see, we are no longer in one dimension. We are involved now in 2 dimensions and must regard it when we determine exactly what kind of answer we're looking for. I'll make the claim right now that 1 times 1 is not the same as 1 squared. This square is a prime base unit in 2D space. All other values in this space will reference this square, even 0. So let's again see 2 times 2, which is really the number of groups applied to 2, the object or increment, and we get 4 as a result on the 1D number line. This is where we were looking for the answer, and this is where we expected it to be. Now let's square 2, because this is really helpful if we want to place tile on the floor of the bathroom. 2 squared looks like this. And 3 squared looks like this. We generally agree that 2 squared equals 4, and 3 squared equals 9. But why? Because 1 squared equals 1 square, like we said, and 2 squared equals 4 squares, and 3 squared equals 9 squares. The answer references the dimension in which we're looking for our answer. Now let's plot these square values. The square root of 9 is 3. The square root of 4 is 2. How do we find the square root of 2? Simple. Move from this diagonal line directly towards the x or y axes and read the value at that point on the line. This may take a long time to do if we use the decimal system and a base 10 number system. We can trim off the eternal stretch of increasingly smaller units attempting to reach the exact point on this line where the square root is actually shown to be, but the rhythm of tens misses the point. And what do I mean by that? First, let's find the square root of 3. Here it is again, in the spatial sense. which is the only sense in which you can conceive of squares, I believe, because we are talking about shapes, squares. Once you square a number, you have turned it into a shape, which requires 2 dimensions, and we now have answers for number questions that can be given in either 1 dimension or 2D space, but we must indicate in which dimension we're looking for an answer in units, and we must indicate which dimension we thus are presenting our answer in and in what units. This is my issue with association. What base prime unit is our answer associated with? In general, math often works with numbers that are not associated with anything but increments, and this works as long as we use proper syntax and grammar to signify that our answer is given in a different base prime unit, in a different dimension, and that is derived from the original dimension that our number question began in. As you can see, square roots sit solidly and rationally on the 1D number line. This is the exact square root, but it seems irrational for 3 reasons. 1, we don't indicate what dimension in which we're looking for our answer. 2, we don't specify what dimension we are giving our answer in with the proper use of syntax grammar. And 3, subdividing our base unit by tens may never allow us to reach the exact, infinitely precise point where the square root of 2 is located. Now, let's look at Terrence Howard's statements regarding the square root of 2. I must keep this very simple because I don't want to misrepresent him in any way. He has listed the following equations for our review. The square root of 2 can be truncated for our ease of use to 1.414. And if we double this number by adding it to itself, we get 2.828. If we cube this number, the result is, if we cube 1.414, the square root of 2, the result is 2.828. So if we double the square root of 2, we get the same number that we get when we cube the square root of 2. Terrence Howard instructs us to follow this loop. Find the square root of 2 on a calculator, and the calculator will show you 1.414213562373 and so on. If you now cube that number on the calculator, the result is 2.828427124746619 and so on. If we use our calculator to divide that number in half, we get 1.4142135623 and so on. Terrence brings these 3 equations to the forefront, as he well should, in order to understand what is going on, and that is exactly what I aim to better understand myself. So allow me to walk us through the rationality of these 3 equations with the help of association to keep local symmetry, and we'll use proper syntax grammar for the sake of sanity. When we double 1.414, we can say that we're moving in a positive gradient along the x-axis, a measure of 1.414 basic increments beyond 1.414, our subjective starting point. We're looking for an answer along this line. Or we can also state that we are applying a factor of 2 to the object of 1.414, recognizing that the factor is a basic unit on a separate scale using the base 10 number counting system. The answer we're looking for is still on the one-dimensional number line, and the answer should still be identified as a unit of increments along this line. If we multiply 1.4 by 4 by itself, that is, if we apply a factor of 1.414 to the object of 1.414 along the one-dimensional number line, we almost get 2 units of increments along this line. This is due to the truncated nature of this decimal, but what is happening here is we are applying a factor of 1.414 to the object of 1.414 increments on this one-dimensional number line. if we now square 1.414 and so on, we get 2 in two-dimensional space. We acted upon the object, but not with a value, but a very specific directive associated with the definition of squares, in that they have 4 equal sides and 4 90-degree angles. When you square a value, you create a square that has 4 right angles and 4 equal sides, each having the value of the number that was squared. Squaring, therefore, is not the same as multiplying a number by itself, necessarily. If the definition of squaring a number is multiplying it by itself, and that definition is accepted by thinking, calculating, overlapping schools of thought, it should be changed and enhanced to make this distinction, that squaring a number is not the same as multiplying it by itself. Let's cube the square root of 2, as Terrence has done. When you cube the square root of 2, on a calculator, you get this answer, 2.82 and so on, which is the same result we saw when doubling the number 1.414. The answer for a question regarding cubes will need to be answered in units of 3-dimensional cubes. I can attempt to illustrate this on this 2-dimensional chalkboard. The number we saw as a result of cubing the square root of 2 is a value describing a quantity of cubes. Cubing a number means we want cubes as a result, and the calculator has been programmed to give this answer in response to our question about what the result of cubing 1.414 is. The answer, 2.828, is accurate and rational as long as we understand the congruency between our questions and answers. Congruency is the third issue I wanted to highlight, and we have sort of fleshed that out a few times here now. Congruency, for me, brings local symmetry. It's comparing apples to apples. Or if we want to use baskets to count strawberries, we remain congruent by not claiming that baskets and strawberries are values, but rather are things. The loop that occurs when you cube the square root of 2 and then divide that by 2 and then cube that result and then divide that result by 2 is something that Terrence Howard poses as a problem or contradiction or evidence of error, or at least that's what I sensed. And it is, I suppose, an error because we haven't flushed out the dimensional aspects that make these answers accurate. The electronic calculators we hold in our hand give answers that exist in various dimensions without specifying which one, and we punch in number sentences without specifying in which dimension we're looking for our answer. Now, I want to plot a point in the third dimension by cubing the square root of 2, which is 1.414 and so on, which again gives us 2.828 and so on. But not because we are in error, but because we are describing that we now have 2.828 cubes. 2.828 squares is not the same answer as 2.828 cubes. 1 squared plus 1 squared equals 2 squares, and the calculator will give you 2 as an answer, and this is accurate. 1 square times 1 square doesn't make sense because 1 object times 1 object doesn't make sense. We need a value. I don't know why Mr. Howard claims that 1 times 1 equals 2, or that 1 squared equals 2, unless he's referring to the 2 line segments along the x and y axes. If so, then he might want to indicate what value of what object and in what dimension his answer is actually being described in. I would like to make the true claim that 1 squared now equals 4. And that's because the 4 in this sentence refers to the 4 line segments bordering the square. I would also like to make a claim that 1 squared equals 1, where 1 refers to the 1 square in this two-dimensional plane. Now I'd like to make the claim that 1 squared equals 4 again, but this time the 4 refers to the 4 equal square subunits within this square. I would like to make the claim that 1 cubed equals 6, where 6 refers to the 6 planes that define this cube. And I'd like to make the claim that 1 cubed now equals 8, where 8 refers to the 8 one-dimensional line segments that define this cube. I could then subdivide a cube and make the claim that 1 cubed equals however many subunits I decided to divide this cube by. In summary, on a calculator, 1 times 1 equals 1 because we apply the value of 1 to the object of 1. On a calculator, 1 squared describes the number of square units we have as a result of squaring. On a calculator, 1 cubed describes a quantity of cubes we have as a result of cubing. When using a calculator, think in terms of 1, 2, or 3 dimensions, and not 4, like time or motion or any other dimensions we may want to say is after 3D. We only keep increasing quantity in terms of volume and area as our exponents increase. Or we watch the one-dimensional marker on the number line increase as it ambivalently counts the values associated with those dimensions. The final challenge I have with Mr. Terrence Howard's recent presentation is that all space is curved and nothing is straight. Fair enough, but curvature only occurs in reference to a straight line. The straight lines of the universe do exist, according to the observations of Walter Russell himself. The universe is a projection of waveforms cast upon wave fields. These fields are straight. The whole universe is a hologram, perhaps projected upon cubic mirrors contained by wave fields. The wave fields and the mirrors are straight and perfectly perpendicular to one another. All curvature of space is relative to the zero curvature mirrors and wave fields of space. Thank you for watching. By the way, I have created an entire course for teens and adults which stands in place of and in brilliant contrast to the 4 years of paltry standard public curriculum. I condense 4 years of high school into 9 months of essential learning for life. Please find a link in the description for a free excerpt from this course, which I call the Full Spectrum Course for Teens. I'm Lori Moore, and I hope to connect with you and your family soon. Take care.